Hey everybody, I'm starting in about 30 seconds, getting some stuff ready. Thanks for your patience. Hey everybody, welcome to episode number 18 of Goldendale Observations, the computer episode. We'll be talking about computers in a bit, and not just of the mechanical variety, not just of the electronic variety. There's also perhaps a living, breathing form of computer, which we'll be talking about. I apologize for the state of my face. I suffered a great fall and have become injured, but I am alive, and we will not allow that fall to stop our show. It was the ice. I went flying across a sidewalk and face planted. Never actually face planted before. Usually I end up stopping myself, but not this time. So I got clobbered. But again, it will not prevent us from learning about science and computers and astronomy and the combination of those things. Anyway, as always, we're coming to you live from Goldendale Observatory, the new and improved. I'm Troy Carpenter. I've been here for almost 8 years now, and I'm happy to announce that I can say with some confidence our facility will be reopening before the end of this year. Now, it could be a lot sooner than that, but I don't want to make any promises. But just so you know, I expect us to reopen in some form or another sooner than later. That might be big news for some of you. Some of you might be tuning into these shows just because you're waiting to come visit in person. I'm bringing this up now because it is going to affect our show schedule. As we gear up for reopening, our schedule may become more sparse. We may stop doing these every week. Maybe we'll do them once a month, or maybe we'll stop doing them altogether. It depends on the workload, what we have available in terms of staff time and resources, and some of the projects that are ongoing here. The big upgrade is finished of the building. There's still some work to be done with some of the exhibits, but for the most part, we're ready to go. And uh, it's a matter of whether or not we are permitted to have large numbers of individuals in the building. What we expect to do, instead of having just a free-for-all where big groups can show up the way they used to, we're going to do an appointment-only kind of system. We haven't rolled that out yet, so don't start any big wild rumors about us reopening tomorrow or something like that, because that's not what's happening. But it could be soon, and stay tuned. We will have more information about that as it becomes available on our website, etc., etc. Okay, so with that, got the chat running here. I see some of you impatient people already making your jokes. Faceplant and all that. Thanks. Yeah, thanks. Um, we let's see what we got going on. 48. Oh, that's not bad. I guess there's some interest in computer science as it applies to astronomy. Um, because there is interest in the room tonight, please ask questions. I say this every show, and I have to say it every show because some of you are reluctant to type. Please ask questions. We prefer that method of teaching where we actually communicate with you and as a result can customize the show to your interests and needs. Yeah. So as I continue to try and fail at starting a tradition, let's try again. Go ahead and ask me a question before I get down to the main topic. And it can relate to the main topic if you wish. It doesn't have to. I'm not going to start until I see at least one question on the chat. I'm looking at the chat. Oh, by the way, while I'm waiting, let's look at our settings really quick. Yeah, we're set at ultra low latency again, and everything works. So hopefully we'll have a quick back and forth without too much delay. Don't see any chat yet. Let's see here. Come on now. I know you're out there. We are here for you. Oh, same one. All right, fine. YouTube looks good. Okay. Someone said something nice. I'm looking forward to another fun observation. So observations, funny thing about that, when you say the word, we tend to imply a person looking, don't we? When someone observes something, we assume that they are looking at information or an event with their own eyeballs. Is that how astronomy actually operates, though, in the 21st century? Are we still looking at things with our eyeballs? What do you think about that? Of course, we look at data, but that data has been collected by apparatuses that have no means of human monitoring. You can't look through a giant research telescope, for example. There is no eyepiece. The data is often obtained in wavelengths that are beyond or below human vision. So right there, it's invisible to us. And that data is also meaningless because there's just so much of it. It needs to exhibit some sort of context so that we can understand it. And the topic of our show tonight, computers, make all that much more realistic. And it's truly extraordinary what computers are making possible in not just the realm of astronomy, but all sciences. And we'll get to that by the end of the show. All right, I see the chat moving now. Is the moon out in Goldendale? Yes, it is. Although I'm not prepared to show it live. We had some issues getting ready tonight, and also I had this thing. So I'm not going to be showing the moon live tonight, and I don't think I can squeeze it in. But it is actually clear out. We had a beautiful full moon a few nights ago. I'm sure you saw it. And how many of you have noticed that in the wintertime, the full moon will often appear incredibly high in the sky? We've talked about this before in previous shows. This time of the year, the full moon tends to be very impressive because due to the tilt of our planet, the ecliptic plane, which is the imaginary line drawn by the orbit of our planet, appears high at night and low at day. So the sun appears low in the sky in the daylight hours, but the moon appears very high in evening hours. So yeah, I have many happy memories as a child of a cold winter night where I look up and the moon feels like it's straight overhead and it's illuminating everything. So we had one of those nights a few nights ago. That was very pretty. So, all right. Well, that's an interesting question. Where does the camera end and the computer begin? So I have gizmos and gadgets, and that's actually not a tangent. Let's talk about that. Let me grab a camera really quick. Oh, I moved it. Hold on. Hold that thought, guys. I'll be right back. We're having all kinds of technical problems tonight. Hold that thought. Thanks for your patience. The universe is exploding. We did not close for business just now. Here comes the lights. The lighting control system just reset itself. All right, as I was saying. So the question that led to that little excursion involved camera technology. And most of you probably know that a digital camera is a computer. So here is a digital camera with an APS-C size sensor. And he asked, where does the sensor begin, the camera end, or something like that? In reality, the sensor is not itself a computer. That shiny object you see in there converts photon impacts into electrical impulses, which are fed through analog circuits, which again are not computers, but eventually counted by digital components, which are part of the computer, but not the computer brain itself. There is a processor in here exactly like a computer. There's RAM, again, just like a computer. The RAM is where the intermediate calculations are stored. There is, of course, also a physical storage medium, the memory card, which is designed for taking the data and recording it permanently. However, that's pretty far down on the chain. However, every aspect of that process, every component in that chain is part of an ordinary computer system. There is firmware, which is rewritable hard to change software. There is, of course, software on top of that, which can be changed easily. That's something you can interact with the screen on the camera. And software and firmware, and then, of course, the hardware work together to allow you to do amazing things like count those millions upon millions upon millions of electrical impulses and convert them into something that a human being would recognize as an image, compress the data, and we'll talk about that a bit, which means reducing its size by finding similarities and averaging them out, and then, of course, finally writing it to the card. And in that process, applying all sorts of filters and special algorithms to improve the quality of the image to your taste or to the tastes of the people who designed the camera. To ask where it begins or ends, it starts becoming a computer once you leave the analog circuits which are connected to the sensor inside the camera. Now that word analog, it's a very important word. Some of you are very familiar with it, some of you are not, as opposed to digital. Tonight we're going to be mostly talking about digital technology. But briefly, just to help understand it, analog technology deals with infinitely variable signals. So an analog signal would be, let's say, a value of 1, or 1.1386585, or 1.2386585. You could have all these intermediate steps, where in a digital system you're dealing with discrete values. And of course, most of you probably know that in modern digital systems, and really all computers built in the last 100 years, they apply Boolean algebra, and again, this is actually on topic. Boolean algebra deals with ones and zeros. So literally a thinking machine, so to speak, that processes information by digesting it as a series of ones and zeros, discrete values. But that digital information, because it is not infinitely variable like analog information, is not real. So when we're talking about images, for example, or audio in the realm of computer science, we're talking about a simulation of reality. And in a way, it's unreal. When you're listening to digital audio, it's an approximation of the original analog waveform. And now, the good news is that computers have become so powerful that those approximations can become extremely high fidelity to the extent that a person cannot tell the difference. And I'm not starting a war here about people that like vinyl records versus CDs, because there are audio formats, for example, that are much better than CDs. Digital audio has evolved so much that it is indistinguishable from the original thing. And the same is true of imaging science. We can produce more colors now on a display, or we can process more colors in a computer system than a human being is capable of perceiving or differentiating with their eyeballs. And this is not new. We have exceeded human vision and auditory senses decades ago. And the change that's occurring recently is cost. So now we can do that kind of thing inexpensively. And by the way, again, this is not a tangent. This has a lot to do with the topic of discussion tonight, which is computer science and how it applies to astronomy and other sciences. You wouldn't think the cost factor would matter that much, but it certainly does. Even if your research budget is big, if you have millions of dollars, well, depending on when you're making the purchase, that millions of dollars can only achieve a certain level of technology based on when you made the purchase. And of course, the longer you wait, the better the technology gets. And so yeah, even though you might have a lot of money, even though you might have deep pockets during a project, that doesn't necessarily mean you're going to have access to the best technology. Or even if you do, that may not be the best technology tomorrow. And many of you might remember, especially in the 1990s, the explosion of computer technology and the immediate obsolescence of everything you bought. So you'd buy a computer in 91, you spent a whole bunch of money on it, and by 93 it was obsolete, which is very frustrating to people. And some people think it's still the case, but it's not. Computers have kind of plateaued in usefulness for ordinary stuff, but they have not plateaued in usefulness when it comes to cutting-edge science, for example. Computer science continues to evolve in the realm of high science, and science reaps the benefit. It's incredible what we can do, and we'll get to that by the end of the show, with these new tools at our disposal. The word supercomputer has to keep getting revised, doesn't it? Your phone would have been a supercomputer in the 1980s or early 90s, which is kind of absolutely amazing when you think about it, that this small battery-powered device that runs on like 9 watts of electricity at 5 volts is able to outperform a giant mainframe that would have filled a room and taken many tens of kilowatts, maybe megawatts, depending on the year, to operate. And what do we do with it? We use it to talk to each other. We use it to look at pictures and videos, communicate Wow, and it fits in your pocket. So I've always said cell phones are one of the most extraordinary examples of the evolution of computer science. And it's important to remember that if we've seen that kind of development in the consumer sector, imagine what we've seen in the professional sector, and it's been even more impressive. So anyway, that was a long kind of tangent, but we covered a few things, and we're going to get into the show. While I've been ranting, let's look at the chat really quick. That's a hard question. What's the best way to find a local astronomer group? Google, Facebook. I tend to avoid those kind of clubs, but I know they still are a thing. But Googling them and Astromart. You might find some people on Astromart or Cloudy Nights. Those are venues where people hang out and talk about space stuff. You might be able to find some like-minded contemporaries to hang out with there. Someone brought up the Perseverance rover. We'll talk about that right about now, actually. Let's see. Is the observatory in the state park? Yes, it's part of the park. It's the facility, the building is within a 5-acre park, which, by the way, is not big by state park standards, but it's not that kind of park. You don't come here to climb a mountain, although we are on a pretty tall hill. You come here to visit the facility or walk around the very beautiful grounds. I have to tell you, it's very pretty here now. After the upgrades we've done, the landscaping is very impressive, and it's a place you might enjoy visiting, even if we're closed, just to take in the sights, so to speak. I'm not encouraging you to climb over the gate. I'm just saying that when things do get back to normal, you can enjoy the park even if we're not technically open at the moment. Thank you for asking. All right. Well, that's fun. Is Goldendale Observatory part of the SETI project? I assume you're talking about SETI at home. This is a very related topic. Those of you who don't know, SETI, the Search for Extraterrestrial Intelligence, relies on computers to sift through just absolutely overwhelming amounts of data. And the more computers you have doing that work, well, of course, the faster you can sift through that data. And so SETI at home is a cool network that allows people to use their regular personal computers to crunch those numbers, looking for alien signals. That's not a tangent. You might want to bring that up again later because it's going to come up as we discuss what computers can do for astronomers and how they can make our jobs easier, and also how they can make, frankly, some astronomy jobs obsolete. Computers are quickly replacing human operators in many ways, and it's not just astronomy. We see that in many sciences. Anything where the word analysis gets thrown around, that's where computers are really good, because they can find patterns, for example, that a human being may not have perceived. All right, so here we go. Where to begin? History of computers. Some people assume that this story starts in the early 20th century. That would be true if we were talking about electronic computers. But one thing people don't realize is that you don't actually need electricity to make a machine which is capable of finding differences, which is capable of determining changes in input data. In fact, this can be done mechanically. So a famous fellow by the name of Charles Babbage, here's a picture of him. Hold that thought. I'm going to put a picture of him on the screen real quick. Charles Babbage was an Englishman, and he invented an extraordinary machine, an apparatus that he referred to as a difference engine, and it was a mechanical computer, and it was able to, let me change that, there you go, now you can see the whole thing. It was able to literally run programs, so to speak, and he realized very quickly, way back in the year 1822, so literally 200 years ago, that his machine could be employed for the computation of astronomical and mathematical tables. Now, that tables thing, this is actually worth talking about. One thing people don't know is that for a long time, computers, which were actually human beings, that is to say mathematicians, would sit down in a room, usually a whole bunch of those people, and they'd work out useful numbers to solve useful equations. For example, you might want to navigate by the stars, celestial navigation. But for you to do this, you needed to know where a given thing was in the sky at a given time. Now, because most people are not super genius mathematicians, they weren't about to sit down and do the necessary calculations to figure out where a given star, for example, should be at a given time. And so they would produce almanacs. This is a fairly recent one. This is from 1946. This is a naval almanac. And if you look, it is simply page after page of tables. Essentially what was being done was this. You didn't necessarily have the resources or wherewithal to do the math yourself, and so you would look up the necessary results for, again, popular equations in a book that you would buy. And almanacs were a very important part of astronomy, a part of all sciences, not all sciences, many sciences. And again, navigation in the 19th century, in the first half of the 20th century. And so people would often do math. They would actually be hired as mathematicians just to fill out those books full of tables. And so that's what Charles Babbage was trying to do. With his invention, he was trying to make it a much more efficient process to crunch numbers and produce these books of useful numbers. Now, here's the thing. Hold that thought. Boy, tonight is like, this is like gremlin night. Everything's broken. All right, so as I was saying, what was funny is he didn't really realize that you could do a lot more with a machine that expedited calculations than simply write books. It's kind of ironic in a way that he was using this machine to fill out printed paper books. There were others who saw his work and realized that this machine could be used on demand, which is important because sometimes you want to do calculations that do not rely on popular figures. Maybe you're doing something new or different. Most famously, the military wanted to be able to quickly do math to calculate ballistics trajectories. But that's kind of an incomplete story. We're going to go over that in a second. But first, I just wanted to briefly tell you the story of this person, Ada Lovelace. You may have heard of her. She was the child of a famous Lord Byron, the British poet. And she was born in the early 1800s. And she was fascinated by the work of Charles Babbage. Her mother did not want her to become a poet like her father because she thought it was a silly job or one that didn't provide enough stability. And so she encouraged her daughter to actually study mathematics. And as she studied mathematics, she became aware of Charles's difference engine and realized that it could be programmed to do useful things. This is arguably the world's first computer program, and it was written by Lovelace way back in the 1820s. She used this to program Charles Babbage's difference engine to do a Bernoulli sequence. It was a famous computational sequence that normally would be extremely time-consuming, something that you have to sit down and work out. So the machine was able to be programmed, so to speak, by her software, and I'm using these terms very loosely, so that it could do a unique on-demand task. And this was done mechanically with no electronics at all 200 years ago. Think about that. We then had to jump forward in time several decades to the early 20th century. And I'm going to get back to that military story. As I said, famously people know about the military wanting to be able to do calculations on demand. You may have heard stories about women who were hired to do computations. Similar to what I was just talking about earlier, they were doing it to fill out almanacs, books. This was done well into the 20th century. People don't realize this. A lot of people think this was like a Victorian thing or maybe early Edwardian thing, but computers as human beings, and by the way, look at the sign, computing division. I love that. Computing section. Not one computer in that room, at least not by the modern standard. These are all human beings. They realized there'd be a demand for, well, on-demand computing, and so you'd have literally rooms full of people who would be working these things out. Now, this is a basic computer science question. Let's see if we understand. Why are there so many people in that room? Why not hire one brilliant, gifted mathematician? This is a simple question, but it does apply to computer science. What do you guys think? Why are there so many people in that room? Answer that. Well, that's right. Someone's saying, reminds me of my trigonometry textbook, lots of tables in the back. Yes, handy, but something you may not need if you have a powerful computer that can do things on demand. So what do you guys think? Why are there so many human beings in that room? Why have so many human computers? What do you think? Let's see if anybody knows. Oh, that's a very interesting answer, and I wasn't going for that, but that's good. Smaller margin of error. It is true that if you had multiple people working on the same problem, then yes, they could compare their results and look for errors, although that was not the primary reason it was done. very often these people were working on different problems. Very good. Well, one person could not do enough calculations. Well, Jim, they could, except it would take forever. So this is just an example of parallel computing, where if you want to process a huge stack of, let's say, input problems rapidly, you simply do more calculations per second, so to speak. And so as a result, instead of one person doing calculations as fast as they can, you have an army of people doing it, and of course you get faster results. This exact concept applies to modern computer science, where if you have, let's say, a processor core that can do a given number of calculations per second, and you want to do twice as many, well, you add another core. Imagine that. This is so completely common sense now, we don't even think about it, but it's kind of novel when you think about it in a human sense. Let's see. Yeah, so those are all good responses. Now, it's worthwhile that we're talking about this today, and I can promise you I did not plan this, but tomorrow is the first day of Women's History Month. And some of you might be aware of the fact that the majority of computers, air quotes, were women. And in the middle 20th century, women of color, no less. NASA famously hired almost exclusively African-American women to work in the background, so to speak, doing these math problems. And it's actually kind of a compliment, in my opinion, if people think you're so precise that you can do math quickly. Of course, not everyone felt that way. And there's a lot of movies, a lot of stories about how these people were mistreated and how their important work was not acknowledged. And the people essentially using the results to do exciting things, well, of course, they got all the attention, all the spotlight. But if it wasn't for the human computers, most of them women, we wouldn't be able to do a lot of the amazing things we did in the first half of the 20th century. So yeah, good timing. Women's History Month comes up. Nice. That's a nice thing to talk about. A very famous woman by the name of Katherine Johnson. You may have heard about her. There's a movie about her right now, actually. And or I think it's out right now. And it talks about her work on the Mercury 7 program, calculating the ballistic trajectories of the first manned space capsules, which did not actually go into orbit around Earth, but did have to land at a certain point in the ocean so that the astronauts could be picked up successfully. Katherine Johnson's work here made that possible. And she was so good at her job that she was often called on to check the work of the electronic computers, which would slowly replace people like her. Not only was she called upon to program these machines or to help design them, but she was actually called upon to check their work. And this is actually something I find interesting, because in modern days, we think of computers as essentially perfect, where they don't make mistakes, because they have so many layers of error correction. And whenever they do make a mistake, they just fail or shut down. You might be familiar, for example, with the blue screen of death, where a single memory error can cause a computer to crash. So we assume that computers are perfectly reliable when it comes to the results they produce, but that wasn't always the case, and computers had to be checked just like a person. So it's like having this person who's incredibly smart with math, but not perfect, not infallible. So a robot, so to speak, doing this work very quickly could sometimes make mistakes, and you had to catch them. Yeah. Another famous woman. Oh, Hal. You're talking about Hal 9000. That's funny. Another famous woman was Grace Hopper. She actually won. She was involved with ENIAC, which was one of the first computers that were electronic, meaning it didn't rely on mechanical relay switches. And she is often referred to as the queen of software, because she is often credited with programming computers that could be reprogrammed on the fly with a program that sits up on top of all the underlying hardware. That's a very important thing. You don't think of computers now as something that would be hard to program, but back in the day, programming a computer literally entailed changing wiring, patch cords, for example. So a human being would have to actually reroute the connections between literally thousands of modules to, quote, reprogram the system. And sometimes a machine couldn't be reprogrammed because it was designed to do a very specific thing. On that subject, this is the thing I wanted to tell you about when the incomplete history of military usage of computers. We often hear the story about ballistic trajectories, where there was a need to calculate the trajectory of let's say, a large round of ammunition fired from some kind of artillery. Computers were popular in that regard because there were so many variables to take into account. you could give a mathematician a problem like that and say, work this out. Where do I need to point this gun so that it lands on this target? And they say, well, that's not that hard. You know, it was a parabola, and there you go. And of course, then they plug that number into their firing sequence, and they miss. And the reason they missed is because there's all these other variables, like the air pressure and the wind and the elevation of the target and the elevation of the gun and the shape of the barrel and the power of the charge and the variability of that and all these things. And a computer is obviously better equipped to deal with all those variables because it entails just such a huge number of math problems. So the military saw this very early on. But there's another use, and I thought this was quite neat when I found out about it. They used this to help bombers navigate during World War II at night. So this is a drawing, but I think it's kind of a neat one. We have here some paratroopers jumping out of an airplane in the dark of night, and we see the moon in the background there. Now, this is quite a neat story, and I only recently learned this. Because they were flying at night, they couldn't rely on landmarks. They had to be able to figure out where they were. Compasses obviously don't tell you the entire story. You might think, well, they would just navigate like you would on a ship. You would think, using the stars. Well, the problem is that an airplane flying at different altitudes, believe it or not, will experience a different view, so to speak, of the sky than a boat at sea level. And computers could be used to help actual aviators figure out where an object should appear in the sky so that it helps them to figure out where they physically are. And they were able to do this thanks to computers like ENIAC, and that was that picture I just showed you, with such great precision that they were able to fly to their target and get right back to their base in total darkness using navigation by the stars and the computer solutions that were provided to them via radio. Again, the reason computers were necessary is because human calculators, so to speak, mathematicians, couldn't crunch the numbers fast enough. I'm not going to spend too much time on ancient history of computers, but are there any questions about this topic? Any questions about the computer thing? Let's see. We now take yes, we now take GPS for granted. Oh, someone mentioned John Glenn asking Katherine Johnson to check the math. That's true. That's a true story, and it's a really cool story. And they had a good relationship. They knew each other well, and he understood. John Glenn understood the value of an expert human. He didn't want to trust these new machines overnight, and he was right to do that. Computers did make mistakes in the mid-20th century, and sometimes you need some clever people involved. James Day points out that bright moonlight would obscure the night sky as well. Not helpful, although that bright moonlight also helps you see a little bit if you're trying to drop bombs on something, for example. What a nice reason to enjoy the moonlight, right? Okay, now, I brought up earlier that, oh yeah, you could use ENIAC to crack codes. I believe that was true. I don't know if ENIAC specifically did that, but they did use computers to try to crack encryption algorithms. You would think that a computer would make short work of that, but of course not all encryption is based on just mathematical subroutines. Sometimes it's based on things like, for example, arcane languages, or strange symbols, or completely arbitrary constructs, or random numbers. And these are things that a computer, especially one of those days, would not be able to figure out. In the modern day, a computer could be helpful in that regard, though, because computers are beginning to exhibit what we refer to as artificial intelligence, because of things like machine learning. And by the way, this is going to come up later. This is actually not off topic. Computers can actually adapt to problems and, amazingly now, rewrite their own code to try to optimize the solution. This is something we certainly couldn't do back in those days. Computers were absolutely in their infancy, at least electronic computers, yeah. Okay. As I said, Mr. Babbage figured out way back in 1822 that computers could be useful for astronomy. Yet this didn't really catch on until the first quarter of the 20th century. We started to return to this concept. I mentioned just now astronomical calculations of positions in the sky, but of course there was a lot more we could do. So World War II had the first autopilot bombers. I wouldn't say autopilot because it was still a pilot flying using relatively old-fashioned methods, but he was being provided more accurate information than he would have been able to obtain in one of these. And by the way, this is not off topic. This is a naval almanac, and this is the exact kind of book. And by the way, the timing is interesting. 1946. This is the exact time or era where they would actually be still using these books, these naval almanacs full of the number tables that I showed you. So for example, that's quite amazing. Here's a table showing the positions of Jupiter's moons. Let's see if you can get, I might be overexposed a bit there. Let's see. Yeah, so you could actually look through a telescope and see where Jupiter's moons were and how they corresponded to the drawing. Amazing. By the way, people were very impressed by the fact that you could essentially predict the future by doing computations. Of course, the problem we run into is, as our understanding of the universe evolves, we realize that the computations are far more involved than we ever thought. So, on that subject. Let's go to the sky really quick. Let's, I don't know, find an object. Betelgeuse. Betelgeuse is a star, famous red giant star. 600 light years away. You wouldn't expect it to change very much in the sky. Yet, as I move forward in time, notice the clock in the bottom, it's quite small, I know. Notice all these numbers are changing. And of course, these numbers are changing because you live on the surface of a rotating planet that orbits a star, and these things wobble. And so an object like a star will actually, of course, change in position from our vantage point. Now, let me go back to that rocking method, This is how it would appear in the sky over the course of a night. Rocking back and forth in this way because of the perspective, like I said, of living on a crooked spinning planet, and you look up, you keep your head straight, you look to the left, you look to the right, but you don't do this or this. And so as a result, things seem to rock back and forth. We talked about this a little bit last week during our telescope show. Now, for a star, it seems straightforward, the calculating solution, because it's based on very well-known variables like our own planet, which we're standing on. But when you talk about other bodies that are moving, suddenly the math becomes much more complicated. Now, I should, of course, point out that stars move as well. But in the context of the early 20th century, that motion was so, quote, slow, so to speak, that it didn't matter very much. But if we go to something like the moon, and by the way, the moon was one of the objects that they used to navigate. There it is. This body is so close to Earth that your position on our planet determines how it appears. So the moon will shift around a bit. We talked about libration a bit last week. The fact that the moon seems to wiggle and wobble, it's because of perspective. But again, that's just an illusion of change based on our vantage point. This is still not the entire story. If you look at the orbit of, let's say, something more interesting like Saturn, we speed up time a bit. Saturn orbits the sun, and we do a good job of figuring out where it should be at a given time, because we've done a very good job over the last several centuries of observing its position and speed. We understand enough about orbital mechanics to expect it to speed up, for example, when it's closer to the sun and slow down when it's farther. But it's not the whole story, because Saturn it doesn't exist all by itself along with the sun. Of course, there are other bodies in our solar system which tug on it. And immediately now you have a problem. Some of you might refer to this as the three-body problem. I prefer to refer to it as the many-body problem. And essentially it is the fact that in the universe you have many bodies pulling on many bodies, and they all affect each other. So you can't figure out where something's going to be with perfect accuracy without taking into account all these variables. Well, this is a big problem, because this means the math problem just got very, very long, and it's going to take human beings an untold number of hours to crunch those numbers. And again, this is why it was recognized that computers could be very useful in astronomy. Little did we know just how explosive the math would become, how many variables would begin to affect our calculations. I just talked about a big famous one, gravitational interaction, but there are other interactions as well that you don't expect to talk about, like we talked about gravity waves a few weeks ago. The fact that some energy is lost via gravity waves, the fact that objects are affected by them, the fact that electromagnetism affects the motions of objects a little bit. You wouldn't think that these tiny nudges, these tiny perturbations would make a big difference, but if we're trying to be precise about how, for example, our simulations, then we need to take these variables into account. And again, this is where you need to be able to do lots of calculations very quickly. The problem was that there was a limitation to how big and how powerful a computer could get, because they used space-hungry components like vacuum tubes. We'll talk about that in a second. Lots of wiring. They had cooling systems because the whole thing got so hot. This affected how much power, so to speak, you could cram into a machine. So we required a few innovations. We needed a few leaps forward in technology to make it more viable. So here's an example of something I like to talk about a lot here at the observatory. Okay, I'm going to tell you what these things are, but some of you might know in the chat. Let's see if you can identify them. These are 3 objects on the screen here. Who can identify what these 3 objects are? And they're all very related to our topic tonight. What do you think? What are these 3 objects on the screen, guys? Come on, someone tell me. What are these 3 things? Tube, well, it could be an amplifier, but it's a tube, a vacuum tube. Transitory chip, I think you mean a transistor. Oh, I see it. I think it was a spell check. Fuse, no. LED, no. Capacitor, no. That's all wrong. No, I'm sorry. Vacuum tube, yes. Transistor. Oh, IC. What's an IC? We'll talk about that. By the way, that was the right answer. Okay, let's go backwards. So since someone mentioned ICs, an IC is an integrated circuit, and it contains multiple examples of the middle thing, which is, of course, a transistor. And neither of those have much to do with the vacuum tube there. Although they may perform similar or identical functions, they are very different in the way they work. Yeah, so let's go over this. Before even vacuum tubes were being employed in early computers, we were using relays. Now, relays are literally switches. Relays are electrically actuated switches. And you guys probably know the states at which a switch can exist. A switch is either on or off, and it exhibits hysteresis in either state, which means it will stay there. So it's either on or off. A relay allows you to actuate a switch without a human finger flipping it on. So relays are electrically actuated switches, and it was understood early on that they could be used to build a computing machine, a difference engine, like Babbage's, that didn't require all kinds of mechanical components and a human cranking something. In reality, you could fill a box with these little clicking relays, and they could be performing logical operations to the tune of hundreds or thousands of operations per second, which in a modern sense is unbelievably slow, but compared to human beings, that's extremely fast, right? Yeah. But the problem with relays is they're moving parts, mechanical component. It has extreme limitations in speed, and also they break. Yeah. Vacuum tubes were thought to be the next big thing when it came to electronics. And when they talked about electronic computers, and I showed you that picture of ENIAC, it was vacuum tube based. Let's briefly fly through what vacuum tubes do. Before I do that, let me see if I have, I thought I had an image. If I don't have it quickly, I will move on. Let's see. Oh, I guess not, darn it. I do have a show I do about Boolean algebra, but I wasn't going to do it tonight for time. But in a nutshell, a vacuum tube is often referred to as an electrovalve in that it controls the flow of electricity like a valve would control the flow of water. I do not like to use water analogies when talking about the behavior of electricity because it kind of opens a can of worms and creates some problems. But yeah, being able to control the flow of electricity was very important in the early days of electronics. It wasn't just a matter of turning it on and off, which would be useful for switching operations, including logical switching operations. It was also useful for being able to control the amount of energy flowing through a circuit using a small control circuit. So a vacuum tube acted like an amplifier, and someone mentioned the word vacuum amplifier here, because a vacuum tube allows you to control a lot of current with a little, and that's a big deal when you want to make weak signals stronger. In a nutshell, the way a vacuum tube works is you have a filament in there, just like a light bulb, and the filament gets hot. The hot filament radiates electrons, but they have nowhere to go because we sucked all the air out. That's why we call it a vacuum tube. The electrons down here at the filament are attracted to the anode. They want to flow through it, to it, but they're prevented from doing so by a grid which intercepts those electrons and runs them back into the circuit. By controlling the voltage on the grid, you can control how many electrons make it to the other side of the tube. So it is truly like a valve, so to speak, an electrical valve, an electrovalve, and that is a term they used to use. Of course, the problem with vacuum tubes, anyone who remembers them, is that they are physically somewhat large. They can be this big, or they can be this big, or they can be this big. They do indeed incorporate a very hot filament, which in addition to creating lots of heat can also burn out just like a light bulb and also consumes a lot of electrical current, which makes it very inefficient. Also, vacuum tubes were hard to make. You would break a lot of them during construction, and just like light bulbs, by the way, light bulbs used to be expensive too for this reason. If you had to throw away a lot of your product out, then obviously that makes the price go up. And they were a consumable item. Even when they're operating properly, they do, like I said, break, wear out, fail, whatever. So they were hot, big, expensive, failure prone, but it did make it possible to construct machines that could perform literally thousands and then tens of thousands and even sometimes hundreds of thousands of logical operations per second. When I say logical operations, we're just talking about crunching numbers, so solving Boolean algebra, series of ones and zeros, converting them into normal, real numbers that we deal with on an everyday basis, like 2 or 3 or 4 or 12 or 98. And the operations per second were fast enough to justify the enormous cost. These machines cost literally millions of dollars. But like I said, even though you might have deep pockets, even though you might be a government or a well-heeled individual who's doing science, and maybe you have a lot of money to throw around, you'd still want to see better efficiency. You want to see the parts get cheaper. You want to see them consume less energy. And so the transistor changed everything, because a transistor does not get hot, or at least it's not intended to get hot. It doesn't have a filament made to get hot. It is not expensive to produce, and it is extremely reliable. In fact, they tend to not fail if you don't abuse them. Transistors can last literally decades. So reliable, cheap, energy efficient. Oh, and I forgot to mention, they can be very small. Transistors are arguably the most important invention of the 20th century. That is a strong statement, but consider what they've done. Transistors made it possible to miniaturize electronics. Some of you might remember the advent of the transistor radio, or at least being little kids, and everyone talks about how incredibly awesome your transistor radio is because it's that big and it fits in your pocket and it's nice and loud and it gets good battery life, etc., etc. Transistors changed everything because suddenly you could perform, for example, digital switching operations instantly, or amplification. So it's an analog or digital device. By the way, vacuum tubes were as well, but it has all the advantages I just listed. And immediately computers started to get much faster, much smaller, much more energy efficient, etc., etc., etc. If you're wondering how they work, a transistor uses semiconductor material like silicon or germanium, which is doped with some conductive material like tin, and this allows it to become controllable in its bias, essentially allowing electrons to only go one way or another, and essentially allows you to create a gate out of this material, which essentially prevents electrons from flowing until you allow them to by energizing that gate. And so, again, it's like a valve, but it's a much more efficient valve that doesn't involve high temperatures and vacuums and glass and whatnot. But it's still an individual transistor, and they might be about that big. And it's like, well, that's not very big. Yeah, but what about if you need lots of them? Because like we said earlier, when it comes to computing, you want to do lots of operations. And we tend to achieve that effect by using lots of components. So we're replacing the human computers with tiny little electronic components. But of course, you're like, I want to do millions of calculations per second, or billions of calculations per second. That might entail installing hundreds of thousands or millions or billions of transistors, which leads to the invention of the integrated circuit. Integrated circuits are clever things. It's a package that can be mass-produced at relatively low cost, although they didn't start out cheap. We'll get to that. And they incorporate multiple transistors, which are often wired in a useful way to perform some useful function. This saves a lot of time. If you're building some kind of electronic component, including a computer, and you want to do a certain thing with it, a very common thing, for example, like a logical AND or 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 NAND operation, where essentially it makes a decision to become true or false based on some other input, well, then you can buy a bunch of these and stick them into your circuit board and you have a computer. So integrated circuits were a big deal because it not only made it possible to condense everything down into these little chips, it also made it possible to build and prototype devices, components, products very rapidly. And of course, this led to the rapid evolution of power, computing power. So we started to see transistors packaged as integrated circuits finding their way into all sorts of electronics, including computers. Now, on this subject, here's a fun history story. The Apollo program had a famous computer called the Apollo guidance computer. And this is kind of a heroic computer because this machine literally got us onto the moon safely. Many of you have probably heard the famous story of Neil Armstrong seizing control after the computer made a mistake and he had to manually land the Apollo spacecraft. It's only kind of partly true because even when Neil took control, he didn't take full control. The computer was still there to control the thrust from multiple RCS modules built around the lander. It had to take into account things like ground radar, for example, which allowed them to figure out not only how high they are, but how quickly they were approaching the ground. So even when Neil Armstrong grabbed the stick, so to speak, and caused them to land a little bit farther down the field to avoid a big boulder range, the computer was still partially in control. And for most of the descent, it was completely in control. But the problem was the Apollo module, the program demanded that every component be small and light and power efficient for obvious reasons. And this computer had to do things that were never done before. And so they made use of the very first practical integrated circuit invented in 1961 by Fairchild Industries. This is the Fairchild Micrologic Type G gate integrated circuit. And this was a mass-producible multi-transistor IC that ended up in the Apollo guidance computer, over 5,000 of them, by the way, which is extraordinary when you learn that they started out being $1,000 each. But the price is actually an important part of the story. The MIT, who was designing the Apollo guidance computer, at one point was consuming 60% of the global integrated circuit market. So one research university, at the behest of NASA and the United States government, was consuming over half of the world's integrated circuits. And of course, as you know, when there's suddenly a big demand for things, a company figures out how to make them cheaper. So throughout the course of the Apollo program, we went to $1,000 each for one of these to $20 each. So we saw a huge price decrease in a decade. This was very important, of course, because suddenly integrated circuits were getting cheap. And so by the early 70s, they were no longer these science experiments, these new-fangled gizmos. They were suddenly a mainstream component, and they found their way into everything, including computers. Yeah. Essentially, computer processors evolved from integrated circuits with more and more and more and more transistors. And like I said earlier, parallel computing, the more transistors you have, the more logical operations you can perform per a given unit of time. Questions about that? We've talked quite someone talks about gallium arsenide. That's another semiconductor. Very good. Let's talk about this a little bit more. Let's hear some questions. By the way, here's a picture of them all installed. So those cartridges or modules that you see there, those contain hundreds of those little integrated circuits I just showed you a picture of, and these are all part of the Apollo guidance computer. Yep. So questions. I'm sure there's some questions before I move on. What do we think? It is extraordinary that this technology has evolved so relentlessly over the course of your life, to the extent, and this is not an exaggeration, this is not a joke, you own billions, with a B, you own billions of transistors. My cell phone here, has over 1 billion transistors in it. Just the processor alone. The processor has 8 cores. Each one of the cores has hundreds of millions of transistors. And they are so tiny that you need a very, very powerful microscope to see them. I find it amazing not that we could conceive of such instruments, but that we can manufacture them. And that is a mind-blowing topic that we're not going to spend too much time on tonight. But if you're really ever interested, learn about chip fabrication. I actually have a few friends who work in the industry, some for Intel and some for AMD. And the technologies involved are mind-boggling. I mean, it's like science fiction technology. We're talking about computers designing computers, computers creating circuits without human intervention. And the human is there just to kind of spot check it because the circuits are so complex that a human engineer couldn't devise them on their own. Yeah. So, and then the creating it using, essentially the circuit pathways are so minuscule on these circuits, that on these integrated circuits, that we have to use lasers of very high frequency so that the wavelength is small enough to etch the tiny little traces necessary to grow the crystals that end up becoming our popular computer processors. Yeah. Okay. Oh, that's an interesting question. If steel was the material of the 19th and 20th century, what is the material of the 21st? I don't know, because we might see the emergence of some new composites. We're already starting. I mean, carbon fiber would be one that I'd obviously say off the top of my head, but there are other materials besides carbon fiber. That's a little bit off topic, so I don't want to get silicon, lithium. Well, oh, I see what you're saying. So not a building material, but just a material that kind of defines the age. Lithium is probably kind of high on that list because it's not only useful in these devices, but it's also useful, of course, in battery technology. Yeah, so maybe. We're only a quarter way into the 21st century, so I don't want to make any declarations about what this century is going to be about. I would like to think it's about electrification. Electricity is a big deal because it can be produced in so many different ways. Yeah, so if we can make everything run electricity and find better ways to produce electricity, then we're going to be in good shape. So anyway, okay, now last chance for questions that are related to what we're talking about. I'm going to talk more in this particular topic, and I'm going to talk about how this applies to modern astronomy a little bit. I'm gonna wait for a question before I move on. I'm going to check my notes really quick. This might be a good time for a little intermission. I'm gonna show you guys a video that entails some current events that you may or may not be aware of. Maybe zinc. That's interesting. So watch this, guys. If those of you who haven't seen this, maybe you're going to see it here first.
We are starting the straighten up and fly right maneuver, where the spacecraft will jettison the entry balance masses in preparation for parachute deploy and to roll over to give the radar a better look at the ground.
Alpha K indicates chute deploy.
The navigation has confirmed that the parachute has deployed, and we are seeing significant deceleration in the velocity. Our current velocity is 480 meters per second at an altitude of about 12 kilometers from the surface of Mars.
Heat shield set.
Perseverance has now slowed to subsonic speeds, and the heat shield has been separated. This allows both the radar and the cameras to get their first look at the surface. Current velocity is 145 meters per second at an altitude of about 9.5 kilometers above the surface.
By the way, if you haven't figured it out yet, we're watching the landing of the Perseverance Rover.
Nav filter converged. Velocity solution 3.3 meters per second. Altitude 7.4 kilometers.
Now has radar lock on the ground. Current velocity is about 100 meters per second, 6.6 kilometers above the surface of Mars. Perseverance is continuing to descend on the parachute. We are coming up on the initialization of terrain relative navigation and subsequently the priming of the landing engines. Our current velocity is about 90 meters per second at an altitude of 4.2 kilometers.
OBS valid.
We have confirmation that the lander vision system has produced a valid solution and part of terrain relative navigation.
Priming. TBA nominal.
We have priming of the landing engines.
That's right, Jim. That's a cool story.
Current velocity is 83 meters per second at about 2.6 kilometers from the surface of Mars. We have confirmation that the back shell has separated. We are currently performing the divert maneuver. Current velocity is about 75 meters per second at an altitude of about a kilometer off the surface of Mars.
TRN 50 Bravo.
We have completed our terrain relative navigation. Current speed is about 30 meters per second, altitude of about 300 meters off the surface of Mars. We have started our constant velocity accordion, which means we are conducting the sky crane, about to conduct the sky crane maneuver. Sky crane maneuver has started, about 20 meters off the surface.
Amazing.
We're getting signals from MRO. Tango Delta.
Touchdown Launch confirmed. Perseverance safely on the surface of Mars, ready to begin seeking the sands of past life. On the surface of Mars, ready to begin seeking the sands.
So, that was
We're
impressive.
starting to straighten up and fly right maneuver.
Let's go back to that part where we see, I find this very impressive. So what we see here are three views simultaneously. So the top view, the upper left view, is the view of the Perseverance rover looking up at the sky crane. The bottom left view is the sky crane looking down at Perseverance rover. And then the image on the right with all the dust flying around, that's the landing camera on the Perseverance rover. Now, yeah, I know, I appreciate their excitement. Now guys, why did I randomly interrupt my show on computer science in space to show you this exciting moment of national pride? Does anyone have a thought as to why I would have introduced this video at this point in the show? Anyone have a thought? What does this have to do with the subject matter? What do you think? What does this have to do with computers? Everything? But explain. What do you mean everything? What am I talking about? It's a robot, and robots are computers. True. That's true. It was entirely run by computers. Very good. You see, Ed up there asked a question about delay. Because Mars is so far away, it takes multiple minutes, and I don't know the exact delay in this particular instance, but it takes multiple minutes for the signal to reach us. And so it would be, and also, of course, our signals to reach the lander. So it would be completely infeasible for us to land via stick, so to speak. You couldn't have Neil Armstrong's descendants sitting there in Mission Control in NASA landing this rover because the signal delay makes that impossible. So this extraordinarily complex operation, which involved firing retro rockets to slow down enough to hit the atmosphere at the right angle and speed. It involved deploying a parachute, involved ejecting that parachute, involved firing rocket engines near the surface of a planet so that a crane could hover in a uniform elevation and also orientation above the surface of an alien planet long enough to lower a robotic probe or rover onto the surface via cables, sever those cables, and then fly off and crash into a hillside. All that had to be done autonomously. This entire operation was performed without human intervention. Of course, very clever humans programmed this machine. But all the decisions that it had to make, by the way, which involved using accelerometer data, radar data, various other sensors, even position of the sun, that's actually a sensor, believe it or not. All these things were factored into the landing sequence, and they were performed flawlessly by a robot, as someone points out. This is a computer. How many of you are impressed by that? I'm impressed by that. Someone says 3 minutes, someone says 12 minutes. It depends. That varies, you know. The time delay between Earth and Mars varies, of course, because of our mutual orbit. So at this exact moment, I'm not sure of the delay, since you asked. You guys can help me out. What day was this? Someone tell me in the chat really quick. When did we do this landing? Because what I'll do is I'll simulate the exact delay if you want to find out. So someone tell me, what day was this that we landed on Mars recently? Yes. Someone tell me, what day did we do this amazing thing? Friday of last week. So what day was that? So was that 19th? Yeah. So let's go back in time. Really? Hold that thought. Okay. 19th. This is Mars. From Earth, 18th. Okay, fine. 18th. Okay, it's now the 18th. Let's look at our numbers. So, distance from Earth, 1.369 AUs. Oh, hold on. I was like, why is my calculator not working? So, 1.369 astronomical units is the distance between Earth and Mars at that moment. Multiply that by 8 minutes, which is roughly the time it takes light to travel 1 astronomical unit. So it looks like the delay was 11 minutes. So someone said about that 12 minutes, yeah. So 11-minute delay. Again, of course, you're not going to land a spacecraft with an 11-minute delay. Can you imagine? So you push the stick to the left. 11 minutes later, it goes to the left. Little do you know, it's already crashed and exploded. Oops. So yeah, we don't land probes landing on aliens' bodies using joysticks from Earth, because that's completely ridiculous. And again, this is where computers come in. But really, this doesn't have much to do with the topic of my show, because ironically enough, as impressive as this operation was, controlling a robot, controlling a rover, controlling a spacecraft is actually a fairly primitive application of computers, because it's really just a simple series of decisions based on various sensor inputs, which are quite straightforward. The numbers are unambiguous, and it can make a decision like fire the thruster for exactly 20 milliseconds, and it knows that doing it a given number of times will result in a certain amount of attitude adjustment. If that adjustment is wrong, of course, there are error codes that will be generated. The system will be able to correct for it. That sounds sophisticated, and I suppose it is, but it's something that you could have done many decades ago, and it's something you could do with any home computer. It's something you could do with even a home game console. For example, I remember the New Horizons probe made some news. This is the probe that went to Pluto. It had a computer that was about the same power as a PlayStation 1 game console. And so I remember the youngsters were like, oh, that's cool, it's a PlayStation 1 in space, but also it seems kind of silly. We're like, why doesn't it have the power of a supercomputer? Because it does not need the power of a supercomputer. And the more sophisticated a computer is in space, the more susceptible it is to damage caused by things like cosmic radiation. Because you see, the more complex a computer, the smaller those microscopic transistors are, as we talked about. The lower the voltage is required to cause them to trigger and create logical errors. In fact, spacecraft have subroutines built into them for recovery from events like cosmic ray impacts that would scramble the memory and cause the computer to lock up. So every time there's an event like that, the probe restarts. Now I'm telling you that specifically because New Horizons experienced a few of those events during its flight where it had to do a hard reset, including at some very inopportune times, but fortunately it didn't jeopardize the mission. But yeah, so we tend to not put overly complex computer brains on probes because these robots really don't need that much computing power. And the more computing power you add, the higher the risk of errors and issues. Any questions about that? Now here's a picture of the Curiosity rover, which is very similar to Perseverance in size. The reason I use this picture all the time in my shows is I love the fact that it has the multiple rovers, and it has human beings standing next to them so you can appreciate how big these are. Think about the fact that this robot, which is the size of a car and weighs about as much, was lowered onto an alien planet by a hovering sky crane, and that extraordinarily complex operation was performed by robots and computer brains. We're almost done with the show. I'm going to go over some of the more deep stuff next. It won't take that long, believe it or not. But are there any questions about computers as they apply to robots? I would argue this is a separate subject from computers as they apply to, for example, astrophysics. Because in a case of a robot, you're dealing with an automaton which has to move motors and open and close various openings and valves and whatnot. But we're not talking about crunching, for example, huge numbers per se. What are the other two rovers? So you might remember Sojourner and, what was it? I should know that off the top of my head. And then there was Pathfinder. Let me hold that thought. Let's see. I'm going to see which one. Yeah, so that cute little one, that's the Sojourner. Right there, yeah. Is my mouse not working? Can you not? I don't think I'm seeing it on the screen. Oh, yes, I am. There it goes. And then the other one, let's see, Mars Pathfinder. Let's see if I can get a picture of that really quick. That's also the same type. So Pathfinder and Sojourner are the little one that looks like a remote control car. The one I forget the name of is that other Mars rover. And if I don't bring it up quickly, maybe someone in the chat can remind me. Let's see. Let's see if I can find it quickly. Anyone, and if you do know, feel free to share it on the chat there. Mars Opportunity, that's right. So that's the Opportunity rover on the left-hand side. Now that's the one that had such an extraordinarily long run, and we kind of mourned it like a person when it died. There, my head was blocking it. Well, literally multiple years beyond its lifespan. A very well-made little robot, wouldn't you say? And in the case of these two fellows, both designs are powered by the sun. As you can see, they have solar panels, which may have actually ended up being what killed this probe, because it literally was covered with dust, and that affects the ability of the solar panels to collect sunlight. But Curiosity and now Perseverance, the one we just showed landing, that is powered by a nuclear battery, a radioisotope thermoelectric generator, very much like the Voyager probes. And so they don't rely on the sun. This is done for two reasons. First, it gives a lot of power up front reliably, but also it provides extra heat, which keeps the probe warm during the cold Martian night. Yeah. Keeping probes from freezing to death is difficult in space science because that cold ground will rob them of any heat that keeps them operating. Yeah. Questions about that? Yeah, you got it. Opportunity. Thank you. Okay, now let's get to the astrophysics a bit. You're like, that sounds boring. Oh, I promise I'm not going to get into it too much. I'm not even that interested in astrophysics myself as far as crunching the numbers go, although we certainly do appreciate the results, don't we? Okay, so let's talk about why computers are no longer a luxury but an absolute necessity when it comes to science. I'm going to show you some amusing cheat sheets that are provided to college students for certain college courses. These are particular ones for Harvard University courses. I don't think it's wrong to show these because you can get these anywhere on the internet. But these cheat sheets, so to speak, are not really providing anything the students couldn't get elsewhere. It's simply a convenient list of handy calculations that entail specific known concepts, known phenomena, known mechanisms in astrophysics. In this case, just radiative processes. So we're talking about just processes that deal with the emission of electromagnetic radiation. And as you're going to see, there are multiple pages of these cheat sheets. Now, what's impressive about this, by the way, those are the 4 radiative process cheat sheets. What's impressive about this is an extremely digested, highly simplified, concise representation of the type of math an astrophysicist contends with when it comes to simulating reality itself as it pertains to space science. We need to understand most of these mechanisms if we're going to create a realistic model. And by the way, that word's going to come up a lot, model or simulation of a given system. In astronomy, more so than most sciences, we have to rely on theoretical frameworks supported by mathematical models, which are simulated, thankfully, in supercomputers. Because, unfortunately, we're often dealing with phenomena that take eons of time to play out. For example, galaxy mergers, which take literally hundreds of millions of years to happen. These are not things you can watch happen overnight. There are, of course, rapid events in space, for example, supernova explosions and their aftermath, which play out over days, weeks, and months. But then there's also these long game phenomena. You have to be able to take into account every conceivable form of emission in this particular instance if you want to create a realistic simulation. Obviously, this is, yes, I'm glad Ed says lots of calculus. Obviously, this involves a lot of math that involves lots of variables. And as Ed points out, Isaac Newton realized way back before we even discovered relativity that you needed a new, better mathematical framework to take into account all the variables that we encounter in space science, including the famous many-body problem where you have multiple bodies affecting each other. Speaking of relativity, here's the general relativity cheat sheet. How many of these do I have? I have 3 of these. I love how they're hand-drawn. I can't believe someone did this. That's one thing I've always admired about astrophysicists and professors and students is standing in front of a classroom writing with a chalk on a chalkboard. They still do that in many lecture halls. And I find it time-consuming and annoying, but they do it because you have to be able to rapidly change or make changes or show people things. And it is an effective teaching aid, although I strongly prefer screens and digital technology myself. But these various equations, again, I want to repeat, are being digested into their most pure form, and yet, as you can see, they fill pages of these cliff notes, so to speak. Consider that it would take human beings, including a whole room of human beings, a very long time to simulate, for example, the behavior of material orbiting a black hole, where all of these, or most of these criteria have to come into play at some point or another. And this is just relativity. Let's go back to electromagnetism, a whole other vein of physics. All of this has to be accounted for. And of course, the more variables you account for and the better your data, the better your simulation is going to be. In a nutshell, this is why we absolutely must use computers when it comes to modern space science, because this stuff is certainly beyond the genius of even the greatest luminaries. I don't care how smart someone is, they're not going to be able to sit down and comprehend all of this individually. They might be able to appreciate and convey the concepts, but they're not going to always be able to crunch the numbers. And if they can, they're certainly not going to do it in a timely manner. Here's the problem. And by the way, this is a good problem. Astronomy continues to evolve. Telescopes continue to evolve. Computer technology, storage technology continues to evolve. Because of this, not only are the math problems getting longer, but we're running them faster and more often, and of course we're collecting more data. And the data collection rate is increasing exponentially. We're talking about an explosion in storage. In the 1980s, we were collecting megabytes of astronomical data per year. And then by the late 80s, gigabytes, 90s, gigabytes, early 2000s, terabytes. Now we're collecting multiple petabytes, so quadrillions of bytes of data monthly in the world's various at the world's various observatories. And imagine crunching those numbers. Of course, this is far beyond a human. So not just computers, but supercomputers are necessary. I'm going to give you some examples of that in a minute. But are there any questions about this in a general sense? This need for computing. Are there any questions about it? And I should add, this is just talking about the math itself. We're not talking about a computer actually, let's say, for example, using a form of imagination. We're talking about a computer literally just solving problems, which does not represent the cutting edge. I'm going to tease you with that. We'll talk about more of that a little bit more in a second. But let me show you some videos of real simulations that we have performed. This is a cool project called the Illustris project, and this project entailed simulating, this is true, 230 million light years of space, essentially a cube, and which was 230 million light years across. If you do the math, you can figure out the cubic volume. And essentially, they created a model universe in a supercomputer called the Cray Hazel Hen, and this is a picture of that supercomputer. As you can see, and many of you have probably noticed, supercomputers often look like lots of refrigerators. And the reason they look like that is because, like everything, we tend to increase our computing power with parallel processing. So if you want to do more calculations, you add more processors. Good question. What currently constitutes a supercomputer? That term keeps evolving based on what the baseline is. And I apologize, I don't have an immediate answer for that question, but I've often heard it's something like 1,000 times faster than a typical consumer CPU. If you want some numbers in this particular device, the Cray Hazel Hen has 16,000 logical cores compared to the 4 or maybe 8 cores that you have in your home computer. By the way, some of you are probably still using computers with single or dual cores. So 16,000 cores. It has hundreds of terabytes of RAM, which is amazing because you think of RAM terabytes, hundreds of terabytes. Think about your home computer. You have maybe 8 gigabytes, maybe 16 gigabytes of RAM. As different observatories collect data, is data shared from one computer to another? It is if you have the luxury of internet connectivity, but not all observatories are placed conveniently nearby, let's say, internet infrastructure. So sometimes we do it the old-fashioned way and actually ship hard drives. I'll hold that thought because I actually have a picture about that. It might help you understand a little bit. I did a show about the we're actually going to talk about this next week. There's a famous black hole. If I don't, what's sad? I apologize. I might not have it as handy as I thought I did. But the hard drives that the data was stored on was actually mailed to the supercomputing center from the various radio telescopes. And the picture I was looking for was actually a picture of those hard drives. Let's see. If I don't find it, I don't have it. I'm sorry about that. So, nope. You know what? This is worth your time. Let's get the internet involved really quick. I'm typing in Katie Bauman hard drives. Katie Bauman is one of the computer scientists who was involved on the project. Here, this is a terrible quality picture. Hold on, guys. Let's see. If I don't find it quickly, there we go. So I see. Oh, there it is. I found it. So this charming picture here of Katie Bauman. And there's various pictures of her smiling. She's one of the computer scientists on the project. And notice she's standing in front of this huge block of hard drives. And notice in the background there are cardboard boxes. So they actually shipped these hard drives to the Supercomputer Center in Germany to crunch the numbers necessary to take the picture you see in the lower left-hand part of the screen there, the famous black hole image. And by the way, this is a good segue to next week. We're going to be talking about this exact project next week. And it was a very exciting story, so definitely worth your time. Yeah. All right, now back to what we're talking about. So the answer is not always. You can't always transmit data in real time because you don't always have fast internet connectivity at your observatory. We're lucky that we have it here. We don't do research here, of course, but I feel lucky because many observatories don't have fast internet. Okay, let me show you what they did using this supercomputer. They simulated essentially the entire universe for several billion years, 230 million light years across. And they were able to, for example, simulate the formation of galaxy clusters. Check it out. This is the kind of big data analysis that's possible because of computing technology. And this is the kind of big data that you simply could never have access to if you were only using human beings to crunch the numbers. Not only because it would take so long to do, of course, but because you wouldn't be able to visualize it so effectively. It's funny, no matter how clever, no matter how smart, no matter how aware scientists are, they still benefit from visualizations, just like we do. When you're trying to understand systems, seeing how they look in three-dimensional space helps you to understand them. What you're seeing right now is the coalescing of hydrogen, which started out at low density and is increasing in density as it collapses under gravity, and forming a cluster of galaxies. I'm going to speed up time a little bit. Let's see here. Every one of those little clumps is a galaxy. See that, guys? Let's slow it back down. Notice there's some big galaxies and some small galaxies. Notice the galaxies interact with each other. They stretch each other out. They distort each other's shape. They end up merging into new, larger galaxies. Notice how their motion is extremely chaotic. This is the kind of thing you would never be able to imagine, so to speak, without, in this case, advanced three-dimensional computer imaging. Let me show you another one. This is from the same project, and we're talking about, in this case, the cosmic web, so to speak. We have this web-like mass distribution, and we see that it clumps up, as we said, into clusters of galaxies. And in this case, we're actually demonstrating the effect the magnetic fields have on light, which is what the colors are intended to represent. And again, this is something you could never do without extraordinarily powerful computers. Now, on that subject, let me tell you a few things about the Cray Hazel Hen, the computer that did this work. I told you it had 16,000 cores. It's capable of 24 quadrillion flops. Now, if you don't know what flops are, that's floating point operations per second. This is more important than operations per second. You might remember those archaic machines we talked about in the beginning of the show that could do thousands of operations per second. Individual operations are not useful if they're not producing an actual result. Floating point operations are useful because we're talking about an actual numerical value which ends up being important in the equation, in the calculation. So that means that a flop actually represents multiple logical operations. So this can produce or perform 24 quadrillion flops, floating point operations, per second. And each one of those flops entails multiple logical operations. That's a lot of math, and yet, even though it can do math that fast, this project took 1 year to finish. So this machine worked on it for 1 year. There are 20 billion virtual particles in this simulation. And like I said, it's trying to simulate it. And by the way, here's the team. Actually, let me, you know what? Let's see the names so you can see who these clever people are. Yeah. So let me get my head out of the way. This is the team of very talented, not only computer scientists, but also graphic designers and other people, astronomers, of course, who worked on this. This is a largely European effort. Here's a simulation of the formation of our own galaxy. Oops. What just happened? There it goes. As you can see, in this simulation of the Milky Way galaxy formation, we see multiple small galaxies merging into larger ones. Notice how they dance. As I was saying, 20 billion particles were simulated in a virtual space intended to represent 230 million light years across. And again, that, if you do the cube, you can figure out the volume. That's an extraordinary amount of variables. Yeah, very good. I like that. Ed points out the many body problem. So instead of the 3 body problem, it's the 20 billion body problem. And what's remarkable is the traditional classical many body problem is purely gravitational. But of course, this simulation is also taking into account electromagnetism, even neutrino emissions. We're talking about different forces of nature, even the energy output resultant from thermonuclear fusion. Look at those galaxies dancing. There it is. There's our Milky Way right there. Look at that. All of these various variables are being taken into account to provide the most accurate, in this case, illustration possible. What's so neat to me about these simulations is that we actually learn how the universe works by watching something that essentially was created by a machine. But of course, it's not created in a vacuum, so to speak. That data is, of course, based on real observations. Because we live in such a big universe filled with so many objects, we have a lot of data to work with. And so it allows us to, for example, study the evolution of galaxies at different stages, which helps inform our simulations. What's remarkable is that a lot of these simulations that are done end up resembling the real thing. Here's a different one. This is a little bit slower. So these are galaxies that are older and are actually actively forming baby stars. Notice they still run into each other. They still collide. What I was going to say is a lot of times, or most of the time, these simulations are actually based on current observations of a given, for example, cluster of galaxies. And what's remarkable is how often they agree with the observed values. I showed you some examples of that a few shows back when talked about the predicted position of a thing by turning back the clock and then turning it forward again, and the computer was right, like 90% correct. It's remarkable. Yeah. All right, let's talk about something more exploding. That's funny. More exciting. An exploding star. This is the simulation of a supernova, specifically a core collapse type 2 supernova. And we've learned some things from these simulations. These supernovas are not homogenized, uniform, symmetrical events. Notice how the event seems to unfold in a let's say, lumpy manner. So you'll see that the shape is complicated. You're seeing the final milliseconds. Notice the timer on the top. The final milliseconds of a star's life. This is something that we cannot be present to observe. We can observe the aftermath. We can observe the emissions before. We can observe the emissions during. But we're talking about what's going on the inside of a star. If it wasn't for these computer models, we would not understand it. Or at least we'd have a worse idea of it. And again, look how it's not uniform. Several million particles were used in this particular simulation, not billion. So, questions about that? Let's go back to the I like this magnetic field one. So we have one last brief topic. We're going to talk about the future of this project, and then we'll be wrapping it up. We're way over time, but this is a long topic. I hope you guys have stayed with me. Let's talk about the future. I mentioned earlier that, what makes this simulation specific to the Milky Way? Because it was. So that particular, not this one, but let me go back to the one you asked about. This one. If you go forward to the end of the video, I jumped ahead there, see that? I'm pausing it. Essentially, that's the Milky Way now, air quotes. So what we often do in these simulations is we collect data now, and then we go backwards in time. In fact, you have to do that very often if you want to understand how something came to be. You go backwards in time. The Milky Way is not alone. The Milky Way is part of a local group of galaxies which all affect each other, and some of them are depicted here. A lot of people don't know the local group contains dozens of tiny, what we call dwarf galaxies. The Milky Way is a big galaxy, as is Andromeda. Both of our galaxies are orbited by companions, like, for example, the Milky Way has the large and the small Magellanic Clouds. We now know that Milky Way has experienced multiple mergers or collisions, in fact, probably well over a dozen. We see the remnants of these galaxy collisions in the form of what we refer to as star streams. Star streams are streams of stars in the galaxy which are all moving with similar proper motion, which indicates they emerged from a common reference frame. They almost certainly belonged to a smaller galaxy which was consumed by the Milky Way. So all those variables are put into the simulation. And essentially we go back in time. You can see the consumption of some of these smaller bodies. See that? Globular clusters, one of the more common or more beautiful types of mysterious space objects, are thought to be the remnant cores from these mergers. Let me show you a picture. This is M13, the beautiful globular cluster in Hercules. And this is most likely the remnant core of a devoured dwarf galaxy. Our Milky Way has about 180 of these. Yeah, interesting. Questions about that? That's a good question. All right, let's talk about the future, and then we'll wrap it up. So I mentioned earlier, I kind of teased you, and I mentioned the fact that as astonishing and impressive as these simulations are, in many ways, it's simply a computer solving a problem. You could argue that it's not technically thinking. It's doing the same thing that mechanical contraption invented by Charles Babbage did 200 years ago, crunching numbers. The future is not simply crunching numbers. The future is machine learning and artificial intelligence. And this is not a, like, oh, someday when we're all flying around in jetpacks and have flying cars. No, I mean right now. We're already doing this. Artificial intelligence is already here. Everyone expects that artificial intelligence will entail, like, weird cyborgs or androids that look like us and talk to us and have personalities, and maybe you make best friends with your alarm clock or something. You're like, wake up, buddy. Oh, hi, artificially intelligent alarm clock. That's what we think because of science fiction. But of course, artificial intelligence doesn't have to look like a person. In fact, it's kind of a waste of time for it to look like a person because we tend to invent computers that are artificially intelligent to perform certain tasks. And those tasks can be of the type that are very time-consuming for humans, but were classically required to be performed by humans because they exceeded that ability of a computer to not think, but simply crunch numbers. So for example, the Galaxy Zoo project. This is a fun thing. The Galaxy Zoo is an online project that's still going on. It's kind of like SETI at home because it encourages citizen science. You mean like autocorrect? That's funny, yeah. Yeah. So, yeah, actually, wait, that's funny. That's an interesting tangent, Ed. Autocorrect is getting smart. It doesn't just generically say, oh, I know that this word is supposed to follow this word. Now autocorrect can actually determine intent, and it figures out where you were going with that sentence, and it makes, believe it or not, actually useful suggestions. I have to tell you, I've noticed this with Gmail and Google now. Gmail, I'm typing an email, and it's giving me these little suggestions as I'm typing about what I might be getting around to saying, and it's often correct. And I have to say, I'm like, normally I hate that kind of thing. It makes me angry, and I want to turn it off, but it's so often giving me good suggestions that really do save time. So if it gives you a good suggestion, you just hit tab and it jumps to the next sentence. Time saver. That's an example of artificial intelligence. That's an example of machine learning. It wasn't programmed by some genius programmer to do that. It programmed itself by observing the inputs and outputs of millions, possibly hundreds of millions, maybe even billions of computer users. It evolves to the problem. Machine learning, and also there's another term for this, neural networks, do this. And this applies to everything. It's not just, in this case, writing. You may have heard about machine learning being applied to autonomous car driving, where it's not just based on what we think a car should do in a given condition or the shape of the road or whatever. It's also based on driving habits. And they collect huge amounts of anonymous, or at least we hope, anonymous data about our driving habits over time. And this leads to smarter and smarter self-driving algorithms. This is machine learning. This dramatically applies to outer space because we have projects that require human insight. For example, the Galaxy Zoo project presents random people. They could be kids at school, they could be actual astronomers, they could be literally anybody on a computer with different images taken by what we call all sky surveys. So you have the entire sky is being imaged over and over again by robotic telescopes now. And we want to classify things, including galaxies. And as you can see, there are different kinds of galaxies. Well, computers are not necessarily good at figuring this out. So a computer might see, an elliptical galaxy like this one and misclassify it as a disk galaxy, or what we would call a spiral galaxy. I don't like this term disk galaxy, but spiral galaxy. It might say an irregular galaxy and incorrectly conclude that it's actually a single galaxy of a certain type, when it's actually, in this case, 3 merging galaxies, for example. So the Galaxy Zoo project employed people, and it's not really employed, they're not being paid, to sift through literally millions of images of galaxies to help the computers to understand what they were talking about, what kind of galaxies they were, because it required a bit of that human insight, a little bit of our imagination to say, oh, that looks a little bit more like this than that. And they even have little training criteria here. See this? Is the galaxy simply smooth and rounded with no sign of a disk? Well then, okay, it looks like this. All right, well then, how rounded is it? No, okay, well it's like, is there anything odd about it? Yes. Is there a feature or a ring? Is it disturbed or irregular? And we end up with the result of an irregular galaxy in this case. Or we say, is the galaxy simply smooth and round with no sign of a disk? And we say, no. Oh, could it be a disk viewed edge on? I'm like, yes. Oh, could it be? Does it have a bulge at its center? And you're like, well, yes. And it gets you down through the matrix, and you end up with a different conclusion. I'm not going to go through this whole thing. You get the idea. The thing is, this is all obsolete because now, with machine learning, with neural networks, with actual artificial intelligence, computers are able to analyze that data and come to the correct conclusion. It was trained by all that human insight and is now able to move on and do its own work. This galaxy classification thing is just one example, and this is a pretty unremarkable one. There's a lot more amazing stuff. Here's a good example. Okay, this is an all-sky image of what you think are a bunch of stars. However, notice that some of the stars have little orange circles around them. Those are not stars. Those are quasars. Now, some of you might know what quasars are. I actually talk about quasars quite a lot on this channel. I think they're fascinating objects. Quasars are the most consistently luminous objects in nature. Their name implies quasi-stellar objects because they appear to be stars but are not. The reason they look like stars, so in other words, little points of light, is because they're extremely far away. The reason they appear as bright as local stars is because they are so extraordinarily luminous. Quasars are the enormously bright accretion disks of material falling into a supermassive black hole at the heart of a distant galaxy. There are no nearby quasars. The nearest one is over 1 billion light years away, with a B. The problem is, again, when we're doing all-sky surveys and collecting data from literally billions of objects, we have to determine what is a quasar and what is a star. It turns out this is very hard to do. There is a difference in spectra between quasars and stars, but it's subtle enough that it does take a bit of concerted effort on the part of an astronomer to tease out the difference. Quasars annoy us in this way, and that's one of the reasons they got the name that they did, quasi-stellar objects. They're also very important. Quasars tell us a lot about the evolution of galaxies in the early universe. They tell us about the behavior of supermassive black holes, etc., etc. So we really want to study them, but again, we have to find them. And Caltech recently applied a machine learning algorithm to this problem, and it achieved something that is truly, truly extraordinary. A 100% success rate. Now that's goofy, that's ridiculous to say because the typical success rates are less than half. So a machine learning algorithm has achieved 100% success in identifying quasars and separating them from black holes, or no, excuse me, not from stars, quasars from stars. Now, something else happened. Because the identification process was so wildly successful, they were starting to find new patterns, new behaviors, new attributes, new characteristics that we were not aware of before because we had dismissed them as noise. We thought it was just noise, but it turns out, oh wait, these are actually different. So machine learning instantly led not only to the incredibly accurate identification of bodies, but the discovery of a brand new kind of object, or essentially a different kind of quasar in this particular context. So computers are no longer just random number crunchers. Computers are now becoming thinking machines, which are capable of actually performing discovery without human intervention. And I was watching a talk recently about this where the astronomer who helped program the system was like, it allows us to be incredibly lazy, where I go into work and I drink my coffee and I wait for the results to show up. In many ways, astrophysicists end up being software engineers because they have to have a lot of insight into how the algorithms work. One thing you don't realize about space science is because we are collecting just completely overwhelming amounts of data now, we have to become good. We have to become savvy about rejecting the noise so that we can retain the useful information and with which we make discoveries. Yeah. This is the future. Essentially, artificially intelligent machine learning neural networks making discoveries for us and discovering patterns that no one ever did. And what's neat is this applies to everyday life too. This is a bizarre story. The same exact algorithms they invented at Caltech for this process were used to diagnose mental health issues. For example, autism. Apparently there's a review process where an interview is conducted with someone who might have it, and they ask them literally hundreds of questions. And the algorithm discovered that only a few dozen questions were necessary. And they were able to answer those same questions with patience and get the same level of diagnostic success. So that's an example of machines being smarter than us, saying, hey, dummy, you don't have to waste their time with 400 questions. Just ask them these 15 questions. Then I can figure it out for you. This is the future, a time where we're inventing machine minds that are better than us. It's funny because, of course, science fiction has been warning us about this for centuries, and we still barrel towards this end because it's important to us. We realize that our clever inventiveness has allowed us to exceed our own limitations, and we figured that out a long time ago. With our inventiveness, long before we invented machine minds, computer brains that could outthink us. So yeah. Humans seem to be intent on doing that, so I'm not going to make any moral judgments about whether or not we should invent essentially brains that are smarter than our brains. But it is both exciting and also perhaps giving of pause. Maybe you'll have to think about it. Is that a good idea? I don't know. So, any thoughts about that? Anyone want to start a philosophical debate about the moral legitimacy of machine learning and neural networks? Yeah, that'll go into the wee hours if we do that. Yeah. This show went way over. I have to admit, I didn't do much preparation for this show. I had no idea how long it was going to go. I'm not surprised it went long, although it is a dense topic, and we did gloss over like all of it. So it is probably a multi-part topic if you're actually going to be very serious about creating, for example, a college course about computerized astronomy. But that being said, let's do 4 minutes of questions. What do we got? Anyone got a question for me, or insight, comment, rant, anything? Great show. I disagree, but thank you. Yes. So I think I'm going to leave this picture on the screen unless you have some special request. Those of you who showed up late, again, the mark on my face was resultant from winter weather. I went flying into a sidewalk. My face met the ground with great force. Hopefully by next week I will be healed and not in pain, yes. But science perseveres. We must persist. No, not true at all. Thank you, though. Next week, we'll be talking about that specific computer triumph, the one I mentioned a few minutes ago, the extraordinary imaging of that black hole. And it's still big news in my mind, even though it's been a few years now. That was an absolute triumph, not just for astronomy, but largely for computer science, because that particular example of imaging was impossible without computers. It would not have been possible by any other means currently at our disposal anyway. So it's an example of computers not being a luxury, but being an absolutely essential tool in the toolbox. And by the way, one of the basic questions we set out to answer tonight, are computers more important to astronomy than telescopes? I would argue yes. You can collect data, but you don't make discoveries at that moment. We don't have that eureka moment of discovery when the data comes in. We have that moment of discovery when we have generated context. And sometimes that takes years. Very often, scientific discoveries occur years after the data has been collected. Partly because we have a backlog. You just have to get to it, which I think is kind of funny when you think about it. And also, sometimes we reanalyze old data using new computer techniques. And this artificial thing, this artificial intelligence, this neural network innovation, this is going to change everything. We're going to be able to go back through decades of old data and make better analysis of it. So you mentioned, thanks, Jeff Anderson. You mentioned layman's terms. I thought this was a fairly advanced show, so this is your last chance, guys. If anything tonight went over your head, it was a bit much, and you want it to be I don't know, simplified even further, let me know, and I will do it right now. So you know what? Actually, iCall reminds me of something I want to make clear. Human landing on Mars will be all computer controlled, or will be manual. Here's the problem. Let's see if you guys can explain it to me. This is not a joke question. This is a real question. Why is it harder to land on Mars than Earth? Go, tell me. Why is it harder to land on Mars than Earth? There's one major difference about that world that makes it harder. What do you think? I'm watching the chat. Why is it harder to land on Mars than Earth? Less gravity? Well, that's helpful. Lack of gravity? No. Low air volume, right. I like that answer. We know Earth better. That's not the answer, but that's a fun answer. Because of the lack of air, Mars's atmosphere is only 1% as thick as ours. As a result, those parachutes you saw deployed, and by the way, James Day mentioned that there was a secret code on the parachutes. Yes, it means do mighty things, and it has the coordinates of JPL. And that's, by the way, in binary. We're talking about binary tonight. So you can convert the red stripes on the parachute into binary and get that do mighty things. But anyway, the parachute is only useful for slowing down the spacecraft, but not enough to land. If they just use the parachute, it would smack into the ground at hundreds of miles per hour, and that, by the way, has occurred. To land, you have to use retro rockets. So imagine trying to land something using rockets pointing down. Those of you who know anything about the Osprey or the Harrier jump jet, and now more recently the F-35, it's very difficult to make a jet hover because you have multiple thrust vectors that have to constantly modulate their strength and their position, and this has to be typically coordinated by a computer because a human being has trouble coordinating all those various thruster outputs. And someone once described landing or hovering a Harrier like trying to balance a knife on another knife if you try to do it manually. Some of you might be aware of drones and how impressive they are. You can buy a drone now for $50, and it's quite amazing how the thing will just like stop in midair and hover perfectly. What people don't realize is the reason that became possible is because of very smart microcontrollers, which are constantly analyzing data from accelerometers and constantly modulating the output RPMs of the various motors, something a human cannot do. Any of you who have ever tried to fly a remote control helicopter, not a drone, but a helicopter, knows how challenging they are to fly. I once bought my brother-in-law one for Christmas, and I couldn't resist playing with it. And I'm like, this thing is really hard to fly. And I'm like, this is not even fun. This is like an annoying challenge. Like, I'm not enjoying this. People love drones because they say, fly, stop, and it does that. The reason it can do that is because of computers. So, and to answer the question, it's hard to land on Mars because you're doing something that requires the coordination of multiple thrust vectors and multiple inputs, something that computers are well suited for, but a human being is not. The exact same problem exists on the moon. Landing on the moon was hard, again, and it required the famous Apollo guidance computer because we were trying to land on a completely airless body, which means we had no, for example, drag to use to our benefit to slow us down. We were completely reliant on retro thrusters to keep us from slamming into the surface or just hitting the surface at a slow speed but tipped over. We don't want to slam into the moon going forward, for example. Everyone would die and that would be the end of the mission. So keeping the lander straight, so it was going down like this, not like this, and allowing it to level out and go down like that. There's a lot of coordination that has to take place. I challenge you, if you can find one of those RC helicopters, try to land it. Try to take off and land with it. You're like, wow, this is really frustrating. Yeah. Any questions about that? Like landing a rocket body on a barge. That's a wonderful example, Ed. So It's amazing what SpaceX has done. They make it look easy when they land these rockets back on Earth. But again, that's only possible because of thrust vectoring controlled by computers. Either the direction of thrust or the output of thrust. They can be throttled very rapidly because they use liquid fuel in the case of the SpaceX rockets, and it's controlled by a fast computer. And it has many inputs at its disposal to figure out orientation of the spacecraft. Yeah. This is something that I want to repeat. Ironically, this is not considered a very advanced usage of computer technology. It's kind of primitive. I mean, like I said, we've been doing it for many decades. Not the same level of complexity as those advanced astrophysics we talked about. Okay, question answer time has ended. It's about time to end the show. I'm going to play that video again just while I talk.
Weird.
Oh. Let's see here. Since we're talking about exciting, brilliant things that humans do. So here's that. There's the parachute with the binary code we talked about there. Did we learn anything tonight? Hope you had fun. I hope the subject wasn't over your head too much. I hope it wasn't boring. We didn't go over much of it, but you can feel free to follow up. We'll be talking about computers again a bit next week as we discuss the black hole thing, so you'll have some more chances then. All right, well, it seems pretty quiet out there. So, everybody, next week, episode 19. If you had fun tonight, if you enjoyed yourself, like and subscribe. I'll see you on Sunday, the 7th of March. Have a good night, my friends.